Everybody, um, what we are going to do now is to check the results of the airplane aircraft experiment that we carried out last week in the classroom. So I am going to share. Mm, mm, mm. Okay, well, this is the table with the results of last week experiment. So we are going to analyze this data and we are going to highlight some important aspects, okay? Okay, okay. So, well, here we have the results that we collected last week. As you can see, there are five different teams. The first one is Viva Aeroméxico. The second one, Los Suavecitos. The third one, it is Green Arrow. Then Los Devis. And finally, Los Avioneros. Okay. Each team had two, three, even four different airplanes, right? So the first team had the Boeing de Fresa and B-2 Spirit, and so on. And these are the measures that we took physically on the classroom last week. So the best airplane for Team 1 was B-2 Spirit. The best distance recorded here was 532 centimeters. Then in the second team, Los Suavecitos, the best airplane was B2, A2, sorry, and the best distance recorded was uh, 612 centimeters, and so on. Okay, so what I did was that I developed MATLAB script in order for me to carry out an analysis of this data and see how well these distances recorded in this table behave. Okay, so let me put the MATLAB script here. I am going to add it here. Mhm. Okay. So here is the MATLAB script. You don't have to worry now about this script. We are going to see that in the very last subject of the uh, experimental design course. So I am going to explain later how I arrived to this code. But for the time being, what you should know is that MATLAB allows you to work with these results of the experiment, and you can also do it in Python. You can do it. There are some different software that you can use. For instance, there is one called Design Expert, and it is explicitly designed to carry out this kind of analysis. Okay. There is another one which is called the Statistical Program for the Social Sciences, which acronym is SPSS, and so on. There are different softwares, but now what I would like to show you is the results and the interpretation um, of this experiment, right? So this is the table, and we are going to analyze every single number. So I am going to put it here. Let me put it in a different way. Mm, 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 mm. 1 second. I am going to put a table, but in order for you to see all the data together, let me erase this and I will put it in a different way. So let me just copy from the okay. I am going to put the table here. Okay. And let me paste this as well. Okay. Okay. Well, here you can see that I am going to try to adjust all this data. This is the original data that we collected in the classroom. All these distances. Also, we have for each of the airplanes, we have the material. Do you remember those that were made with bond paper, and others with folder, others with PET, and so on? So we have the material, the length of the airplane, we have the width, we have the height. Okay, so all this information is put together, and we arrive to these results by means of this MATLAB script, right? So what we have is that we are trying to predict the distance based on the material and then the dimensions of the airplane. In this case, the length and the width. So we have these results, and these are the coefficients for this formula. So let me write the formula. In order to predict the distance should be equal to the first number is the intercept, which is the free term. It will be 35, 31.1. Then I have to put the following number, which it will be minus 130.56. This is multiplied by the material times the material. Then minus, I put the following estimate, it will be 89.969 times. In this case, it will be the length which is this in Spanish will be largo, then minus 215.6 times the width plus I should add this quantity and I should put 7.7083 times, and I have to multiply both length times the width. Okay, so this will be the regression model resulting from the analysis that we have just developed. Okay, so let me record this. So I am going to open an Excel file. Okay. Okay. Well, and I am going to share the Excel. Mm, mm, mm. Excel. Okay. So what I am going to do is to put here the coefficients. Okay. So we have, these are copied from the table. So this is the intercept, which is 3531.1. Then I have the material. So I am just copying these quantities, material, which is minus 130.56. Then I have the length, which is minus 89.969. Then I have the width. In this case, the quantity is minus 215.6. And finally, I have the multiplication, which is length times width. Okay. The coefficient here is 7.7083. Okay. This is the model. Okay. Well, put the model here. I am copying. Mhm. Okay. Perfect. Okay. This is the model, right? Well, what I am going to do now is to see how well this model predicts my distance. Okay. So Let me make it smaller. Okay, this is the model, okay? And these are the coefficients. So what I am going to do is to put here the input data. So I am going to put here the material. I am going to put here the length. I am going to put here the width. Okay. So for instance, let's see, let's suppose that I have material, it will be 4, length, it will be 30, that is in centimeters, and the width will be as well in centimeters, 12. I suppose that it is 12, okay? So what I am going to do is to carry out this product. So I am going to put here material times 4, this is the product. Then length, it will be this coefficient times, and I'm going to put here the length. Then I am going to multiply this coefficient width times this width. And finally, I am going to multiply this coefficient times both length times width, okay? And this is direct, this quantity remains constant, so it is exactly the same. And here is going to calculate the distance. So the distance is the sum of these quantities, okay? So close the parentheses. This is, so the predicted distance with this model for this airplane, which is 4, 30, and 12, is 497 centimeters, okay? Let us check. Let us check. So I am going to put this table here. This is the original table, okay? So this B2 spirit, I am going to put here B2 spirit. Was made with the material number 4. You can see here, this is material number 4. The length is 30 centimeters, so material is 4. I am going to put it in bold. Then the length is 30. I am going to put it here 30. And the width is 12 centimeters, okay? So this is 12. With this data, the predicted distance, I am going to put it here in black, and this is the distance. So it will be, the distance is 497 centimeters. And in real life, this measure was 464, 533, 498, and the best was 53. Check, this is exactly the quantity that we recorded in the table, the second one, right? Which is 498. And here the model is predicting 497. Let us see with another airplane. So team number 2, Team number 2, the airplane was A2. Okay, and let's see what is the data for this airplane. Airplane A2 is material is number 2, so I will put material number 2. Then the length is 20 centimeters, so I should put here 20. And the width is 15, okay? 15. So the predicted distance is 549 centimeters. Let us see the real data. This airplane flew 612, 388, and 612. So look, this is not so exact in this case. In the first case, it was very exact because it predicted exactly the distance that the airplane actually flew. But in this second case, this is not so exact because it is a little bit farther from these real distances, right? Anyway, let us see the third team. The third team, the best airplane was SF-26. I will put it here. SF-26. Here. SF-26. Okay. Let us see the data, the input data. These are the independent variables. Remember, the independent variables are the material, the length, and the width. And the dependent variable is the distance. The distance depends on the other three variables, okay? So let us see. For this airplane, material was number 2, length was 30, so I should put 30 here. And the width was 10 centimeters, so 10. Based on this model, the predicted distance is 727 centimeters. And let us see the real data. This was the very winner airplane. Do you remember the one that was thrown 3 times, and all the times it was close to the wall, to the classroom wall? This is the same measure for the tree. It was 795, 795, and 795. So, and look, the prediction is that this airplane with these dimensions and this material would flew 7 to 7. So it is very close, right? It is kind of close. So my model is working okay in this case. This is the model. Remember, this in bold in black bold is the model. Let us see the following for team number 4. For team number 4, the best airplane was Birney, which is Birdie. I remember Birdie. It was Birdie. And let us see the input data for my model. It will be material number 2. And in both cases, length and width, it is 14. So length 14 and width is 14 as well. The predicted distance is 5 meters, approximately 5 meters. And let us see the actual data. It was 593, 756, and 756. So perhaps for the very first measure, this is close, but the others are far apart, okay? They are not so close. And finally, let us see the last team. The airplane was Avión 2. And the input data, the independent variables are material 2, length 22, and width 14. 2, 22, and 14. The predicted distance is 646 centimeters, okay? And let us see the real data, which is 795, 598, and 795. This is as well one of the airplanes that flew until it crashed in the classroom wall, okay? So this is the last team. This is the predicted distance, okay? So as you can see, let me save this file, save as here. Let us put it in the download. Okay. Distance prediction model. 23 February 2026. Okay. Save. Okay. I am going back to my Word file. Do you have any questions? Do you have any questions? While I am changing back to the Word, if you have any question, please feel free to ask. So let me stop sharing. I will put now the words. I am back. So this is the data that we use in the Excel, and this is the MATLAB script. This MATLAB script, well, just quickly, you have different measures in this table. And what you should do is to put these measures, for instance, here in material, okay? In material, you put 4422. Each of these quantities correspond to the data that we collected in this table, okay? Again, don't worry about that in this moment. You should learn about how to do this in the future at the end of this course. But for the time being, I would like to show you where are we going to. This is our goal, to create models that predict. And in artificial intelligence, if I have this model correct, so imagine that this is my model, this. I can predict. One user can say to me, "Oh, I want to know how far or what is the longest distance that my airplane can fly. If it is made with bond paper, it has a distance, a length of 30 centimeters and a width of 12 centimeters. And because my algorithm has this model, I can predict exactly how far this airplane is going to fly. That is the idea, okay? That is the idea. So here, and that's why I have to design an experiment, okay? Design it very, very good, in a very good way. So here you can see that the number of observations is 14. So this is 14. The errors degree of freedom, this is 9. This is the root square error, which is 148. I will explain each quantity, don't worry. I am just saying now, but I am going to explain every quantity now. And the R squared, which is this is the indicator that tells me how good this is for predicting my distances. The closer to one this quantity is, the better the model for me to predict. So if I have a model which is one, exactly one, this is a perfect model. This model will predict exactly the quantity of centimeters that my airplane is going to fly. But we can see here that it is just 0.37. So this means that it is only 37% good, this model. It is not 100% good. It's just 37% good. Okay, I will explain in a moment. And this is the adjusted R squared. And these are the some statistics that I have to calculate to see how good my model is for predicting the distance. Okay, so then the next step, I will put here this some other result for a different model. Mm, let me copy from here. Okay, this was a model that had only linear terms. Okay, all of these terms are used in the linear way, but in this second model, I am going to try to develop a better model. Let's see if I can get a better model than the first. And this is going to take into account this power to the second power. Okay, I am going to put these dimensions, and I am going to use powers in order for me to see whether this is a better model than the first one. And again, I have these coefficients. This is the estimate, this is the material, and this is the width. Okay? So what I would like you to do now is, please, you in Excel, develop this model. Okay? You are going to do exactly what I did. You are going to copy this coefficient. Let me put it in the WhatsApp for you. I am going to take a photograph. Okay. Okay. That is the photograph. And these are the data. Okay, so what I am asking you is, please carry out exactly the same exercise as I did in the Excel file, but now with this new model. Okay, so you have, in this case, the intercept is 0, the material coefficient is -36, the length coefficient is 133, and so on. And the data for the airplanes I have put as well in the WhatsApp group. So I will show you the Excel file. So here we are. Okay. So please try the 5 airplanes, but now with this model, and see how good this prediction of the distance is. And please write the distance for each airplane in the chat for the teams. In the teams, you have to put the distance predicted with this model, with this new model. But for the airplane B2 Spirit, then for the airplane A2 SF-26, Birney, which is Birdie, and Avion 2. Okay, is it clear? Is it clear what you are going to do? Any questions? Okay, let's take 15 minutes to carry out this exercise and I will see you back at 5 p.m. Okay, carry out the exercise and I will see you back at 5 p.m. please. Okay, it is 5 o'clock. Do you already have the results for this second model?
In my case, give more time, please.
Okay. Do you need more time? It's okay. I am going to give you 5 minutes, 5 more minutes.
Teacher, I have a question.
Yes, please. Go ahead.
Do we need to use the part that says length rise to and y rise to as well?
Let me see. We are going to do it here. Let me mm, let me copy the model will be the following. So it will be. I am going to share my Word. Word. Okay. So what will the model look like? Well, this new model, this quadratic model, will look like this. So it will be distance equals 0. I am not going to put this 0 because, well, if you add 0, that it is exactly the same result. So I am going just to ignore that quantity. But then I have to put minus 36.675 times material plus 133.83 times length plus 0. Again, I am not going to put the following coefficient minus 0.2646 times. This is you have to consider the two dimensions, length. Here is a G missing times Y. This is the following point. Then we will have to consider minus 3.1387 times the square of the length. So it will be length, but to the second power, okay? To the second power. So it will be, I will put it like this. And then the second power. Okay. Okay. Then we have to consider minus 3.2749. Oh, this is here. Let me get rid of this. Okay. Minus 3.2749 times, and this will be the width again to the second power. To the second power, okay? Here we are going to put 2. Okay. Okay. Very good. So let's go back to the Excel. Any questions about this model? How I get this model? I am just taking these coefficients for this model, which is a quadratic model because it is considering the second power of the length and the width. Okay, this is a quadratic, and the other one was a linear model. The one that I put at the beginning, this is a linear model, and then this is a quadratic model. We could also develop a cubic model, which is to the third power. It will be a cubic model, but now we are going to work with the quadratic model, the second power. Okay? Well, I am going to Excel. Okay. So let us do something. I am going to put this down here. I am going to leave this there, and I am going to copy this. Okay, this is our new model. So I am going to show you here as well. This is the quadratic model. Okay, so let us carry out the numbers. So this is my input data. This is going to be with green. I have to put this data which is in green, okay? Green. And the result comes here in, let's say, in yellow. This is the result. It will be in yellow. Okay. So with the new model, what we will have to do is the following. We are going to put here material and the coefficient, which is minus 36.675. Okay. This is the coefficient, this one here in this part of the equation. Okay. Then the following will be the length, and the coefficient is 133.83. Okay. Then the following term is 0. Then it will be length width. I will copy this. Length width, and the coefficient is minus 0.2646. Perfect. Then the following, it will be length, but this is to the second power. So we could put length times length, which is exactly the same. And the coefficient here is minus 3.1387. And finally, we have the last term, which is width times width, which is exactly to the second power. and the coefficient is minus 3.2749. Okay, so let's calculate the distance now. I will put distance 2, which is the model, the quadratic model, and this will be distance 1, the linear model. I can have a power model, I can have a polynomial model, I can have a exponential model, a logarithmic model. There are so many models, okay? As a engineer in artificial intelligence, I have to look what is the best model. And the best model is the one that I am going to use, okay, for my artificial intelligence algorithms. Okay, so let us do it. So here is the distance that will be put here, and centimeters that will be put here. Okay, so let us carry out the exercise. This is centimeters. Okay, so first I will have to multiply this coefficient minus 36 times the material, which is 2, and then I will put this equals this coefficient times the material. Okay. Then I will have to multiply this coefficient times the length. The length is here, okay? Then I will have to multiply this coefficient times both the length first times the width. Is it okay? I am just following the formula that is put down here, this formula, okay? Well, the following quantity is this coefficient times length times length, because it's to the second power. Okay? And finally, this is this coefficient times the width to the second power. I can put the second power like this in Excel, okay? Or I can multiply 2 times the same quantity, which is exactly the same result. Here we are. So when we add up all these quantities, the sum is the result, the distance, the predicted distance. Let us do it. This is enter. I am going to put it in another color, in orange. Okay, this is distance number 2. Perfect. Okay, so let us compare the two of the models, the two models, the linear model on the one hand and the quadratic model on the other hand. Okay, so with the first airplane each B2 Spirit, let us put it here, B2 Spirit, enter. So what is the input data in green? Material is 4, Then I have 30 centimeters length, and I have 12, right? White. 12. So look, this is 497, and this is exactly 497, and it corresponds to this measure, okay? The second, the one, two, the third one, the number three in the record that we carried out last week in the classroom. This is the thing. So let me do something. This is B2 spirit. Okay, I am going to put this in my Word. You cannot see, but I am doing it now. Then let us go to the second airplane, which is A2. Airplane A2. What is the input data? Material is number 2. Number 2. Then the length is 20 and the width is 15. Okay, 20 and 15. Okay, so look, the predicted distance for the first linear model is 549, and for the quadratic model, it is practically the same, 548. I am going to put this in the Word, but I am going to put another thing. I am going to put the actual distance, which is, let us put 5 to 5. I am going to put the closest. So it will be 5 to 5 centimeters. I am going to put this. This is the one that we recorded in real life. So let me put another color. Let us see in blue. Okay. So I am going to copy this. Okay. And I am going to put it here. Okay. Well, let us go with the first, the third. It will be SF26. 26. And the input data is material 2, 30, and 10. 2, 30, and 10. Okay. And what is the actual measure? 795 for the tree. 795. That will be the real distance. But this model is predicting 727, and this is again 727. So let us copy this and put it in the Word file. This is for the third airplane. Okay. Let's go for the fourth airplane. So the fourth airplane is the one called Birdie. Birney I am going to put. And what is the input data? It's material 2, 14, 14. Okay. 2, 14, and 14. And what was the actual measurement? It was 593. Let us put 593. 593, okay? 593, okay. But look, this quadratic model is also giving me the same value of the linear model. Here I am going to print this part of the screen and put it in my Word file. Okay, and finally, the last, it is called Avion 2 2214. Okay. Avión 2. This is 22. And the other was 14. It's okay. And the actual distance was, let's say 598. Let's say 598. Okay, perfect. Okay. I'm going to put this in the Word file. Okay. Just one thing. Let me, for the first airplane, I didn't put the distance here down there. So I am going to repeat it and replace this image. So the first one, B2 Spirit, B2 Spirit. And it was made with four, material number 4, 30 and 12. Okay. 30 and 12. Okay. Enter. And the actual distance was, let's put 498. This is very precise. 498. Okay. So I am going to put this here. Okay. Okay. So I am going back to the Word file. This is Word. Okay. Okay. So look, in this case, in the quadratic model, I have different coefficients for the combinations, length, width, length with width, length to the second power, and width to the second power as well. Okay, these are the coefficients that were calculated for this second model, the quadratic model. But look, the precision is very similar to the one that we had already analyzed, the first one. So in artificial intelligence, if two models are giving me exactly the same results, I would prefer the simpler. Okay, there is a acronym in English. I will write it here, which uh, it says KISS. KISS. It means keep it simple and stupid. KISS means keep it simple and stupid. I don't want to have a very complex model. I would prefer to have a very simple model, okay? And if they two are giving me exactly the same results, I will choose the one that is the simpler, okay? I will use this acronym KISS. I will keep it simple and stupid, okay? So let me erase this. I am going to leave it there. I like this thing. Okay. So let's go back to analyze these results. So with the second model that I have the second power, this is a quadratic model. Look, for the very first airplane, the B2 Spirit, the predicted distance is with my first model 497, and with the second model it's again 497, and this is very exact. These two models are excellent for predicting the distance of this B2 Spirit, right? Because the actual distance, the real life distance, was 498. Okay, then for the second team, airplane A2, the actual distance was 525, but the first model predicted 549, and the second model practically the same, 548. Okay, so these are very similar. What about the team number 3? In this case, the airplane was called SF-26, and these are the predicted distances 727 and 727 as well, but the actual distance, the real life distance, was 795. Okay, so you can see the two models, both the linear and the quadratic model, are giving me exactly the same with different coefficients, but they are giving me the same result. Okay, the Birney airplane, with the first model, I have 502, and the second as well, 502. And the real life distance was 593, okay? And finally, in this case, in the Avion 2, I have the predicted distance was 646, and the second distance was predicted as 646 as well. But the real life distance, the actual distance was 598. Okay, so as you can see, the two models for this particular data provide exactly the same uh, quantities, the same result. Okay, they provide exactly the same result. Okay, so which one will we choose? We choose the very first model, the linear model, because that is simpler. It's a simpler model. Okay. So let us see. I am going to put here. In the first case, what model are we estimating? I am going to put it here. This is model number 1. This is the model that we are estimating. In design of experiments, we put this general model. This is the general model, and we have to look for the beta coefficient. Okay, this beta 0, beta 1, beta 2, and so on are the coefficients that we are interested in when carrying out all these calculations. This is again the ones that we are looking for when we are carrying out these experimental designs. So in other words, The flight distance depends on material length, width, and the interaction between length and width. Okay, this is the meaning of this formula that we are trying to establish. Okay, so the second point, let us put it here. The second point, uh, how are we going to interpret these coefficients? Okay, the intercept has, well, it is a very big coefficient, 35, 31, okay? So this has no a physical meaning. We cannot interpret that this value as such, because that would mean that everything else is zero. If I have in this model, in this one, material zero, length zero, and width zero, the only term that will survive that operations is the very first 35, 31.1. Okay, that will be the distance. That will be the minimal distance that you should expect for an airplane. Okay, but this doesn't have any meaning in the physical terms, because you cannot have an airplane with a length zero and width zero. That would mean nothing. Okay, it means that you have nothing. You don't have any plane at all with these characteristics. Okay, so that airplane doesn't exist. That airplane doesn't exist. I will highlight this affirmation. So you should remember, when variables are not centered, the intercept is often not meaningful. So this is one thing that we should be very careful about. Okay, so let us now interpret the following coefficients. So I am going to put here the second explanation. Here. Okay, so what the following coefficients mean? Material coefficient, it is minus 130.56, and this has a probability of 0.10. Okay, let me divide this screen. Okay, okay, and I am go up. Okay, so the second coefficient is minus 130.56. You can see it here. And the p-value is the probability. It's 0.10889. Okay, well, here we can put that 89. Okay, perfect. So how can you interpret this value? Well, when you change the material, the distance reduces about 130 centimeters. Okay, that is on average. That will be the meaning. But since the p-value is greater than 0.05, which is the critical value for this um, analysis, this is not statistically significant. I will show you a very good design experiment, and we are going to see how these values change. But for now, just keep in mind, this minus 130 means that, for instance, if you have a bond paper airplane and you throw it, it will fly some meters, okay? But if you change the material, let's say that you put a folder, then if I have the same through, this will fly 1.30 centimeters less than the other. Okay, that means this value with the material. Okay, so for instance, the first airplane will fly 5 meters, let's suppose, and just changing the material, the following airplane will fly 3.70 meters, okay, which is 1 meter and 30 centimeter less than the first one, just by changing the material, okay? That is the meaning of this value, of this coefficient, okay? Now, here are some notes because with this information, we cannot say with total certainty that this is happening, but this is a sign that we can interpret now in this way, okay? So let's go for the following interaction. Okay, I am going to put it here. Here. Okay. Mm, 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 mm. Okay. Let's go for the following interaction. Okay. Look. Now we are going to look at the interaction between length and width, okay? Is the last coefficient. Sorry, length and width. It is length and width, the following two variables. Okay. Well, in this case, you can see the p-value. It is approximately 0.6. I am going to put the quantity 7065, and the other one is 0.622. So it is from 0.62221 to 0.67065. This is the values. I am taking these values from this table. Okay. So this means that the length alone does not significantly explain distance. I cannot predict the distance in this experiment that we carried out in the classroom just by having the length. It doesn't matter if it is a short airplane, it doesn't matter if it is a long airplane. I cannot predict the distance from this experiment, okay? And the width is exactly the same. Width alone doesn't significantly explain distance. Again, it doesn't matter if I have a very, let's say, a wide airplane or a very long airplane in another direction. It doesn't matter. I cannot explain the distance that this will fly. Now, what happens with the interaction between length and width. This is the last one, okay? In this case, the p-value, you have to look at the p-value. The p-value should be less than 0.05. In this case, you don't have such a number, okay? So this means that it is not significant. And how can we interpret that? There is no statistical evidence that the geometric combination drives performance. So we cannot conclude now that combining one length with one width, this is going to be a better airplane than another with a different length and a different width. We cannot conclude that because we have a very limited sample size. So it is just 5 airplanes. So it is a very short sample size. Okay. Well, so far, do you have any questions?
No, teacher.
Okay. So let us put some conclusions here. Okay. Well, what are the conclusions of the experiment that we carried out last week in the classroom? First of all, we have 3 fundamental lessons. The first one, poor experimental design produces unstable models. So you can see that somehow the model predicts the distance, but it is not very accurate. It is not exactly the distance that you were expecting, right? That is the first. So this was because actually we didn't have any experimental design. All that I did was telling you, please design an airplane, use the materials that we have at hand, and that's it. And you just decided, well, we are going to use bond paper, we are going to use a folder, we are going to use a PET, we are going to use cardboard, and so on. But we didn't have a plan. We didn't have an experimental plan. So we just built the airplanes and we throw them. We recorded the distances, and that's it. Second lesson, more variables do not guarantee a better model. Do you remember these 2 models? This is one model. Look, this model has 1, 2, 3, 4. It has, let's say, 5 variables, okay? These are the rows of the table are 5. But what happened with the second? In the second, how many do we have? We have 1, 2, 3, 4, 5, 6. We have seven different variables. And it doesn't mean that we have a better model. In fact, these 2 models gave us exactly the same distances, the same predicted distances. And we have more combinations here, more terms. But the model worked exactly the same. Okay? And the third is that sample size matters. Okay, it is very important to have more samples in order for us to have a better model, better artificial intelligence model. Okay, if I just have a few samples, my model is going to be very poor, is not going to be powerful. But if I have more samples, if I have many samples, my model, it will be very powerful. It can predict very good distances because it has got a lot of information internally that allow me to predict better. Okay, so in engineering terms, this was not a formally designed structure design of experiments. This DOE means design of experiment. Okay, that is the acronym for design of experiment. So we didn't design it at all. So it was just like a feeling. We did all a feeling. Oh yes, I feel that this is good. Let us fold it and let us construct this airplane. That's it. Then it was a set of trial runs that is reflected in. There is a large residual variance. There are high p-values. We could see in this table. These p-values are very high. You should expect, again, values lower than 0.05, which means 5%. 5%. This is the critical value, okay? We are going to show in a minute that. And there is a weak overall significance. So here the very last conclusion is that the problem is not the mathematical regression, the model. The problem is the experimental design. If I want to have a very good intelligence, artificial intelligence model, I have to design properly my experiment. Otherwise, I will get something, but that doesn't guarantee that that is going to predict correctly what I would like to predict. Okay? Okay. So any question? Any question about this? Okay. It is 5:46. I will see you back at 6 p.m. to close the explanation with a very good design experiment with the airplane. What will be the ideal for this experiment? I will show you at 6 p.m. Okay? So don't be late. I will see you in 15 minutes. Thank you so much. Take a break, some coffee break. Thank you. Bye. Okay, I am back. Like the Terminator film, the Schwarzenegger. I'll be back. Okay. Uh, does anybody have any question so far? So let us go to the uh, how can we design a good experiment? What is the strategy to carry out a good experiment? What would be the strategy in this case to design a very good experiment? So let me show you. I am going to share with you. Okay. This will be the proper design of the experiment. Okay. Okay. So creative aircraft maximum distance, perfect. So we will have to design a 2 to the third power full factorial experiment. That will be the correct strategy. Don't worry about don't understanding what this means. Don't worry. I am just going to show you the big picture. Okay, I am going to show you the big picture, and then during all the term 2026A, March, April, May, and June, we are going to see this in detail, okay? But now I would like to show you the very big picture, the big frame, okay? So we will have to design this kind of experiment. How is it made? Okay, we will have three factors. That is the exponent here in this equation, 2 to the 3 power. And the first factor or variable would be the material. And we have two levels, bond paper, and the folder, okay? Bond will be represented by number 1, and the folder will be represented by number 2. Then we will have the length, and we will have two lengths. The low level will be 30 centimeters, and the other will be 20 centimeters. And then we will have the width, okay? It will be 16 centimeters with a height of 3, and the other level would be 10 centimeters and a height of 5. So these are the three factors that we are analyzing, and each factor has two different levels. That is the meaning of these two. The two means the two different levels, and the three means the factors, the number of factors. So if you carry out this, 2 to the power 3 is 8. Why? Because 2 times 2 is 4, times 2 is 8. In total, 8. 8 different combinations. So the design type has precisely 8 different combinations, and we are going to have 3 different throws for each airplane, 3. So that means that we are going to have 8 times 3, that will have 24 observations, okay? So in this case, because observations are greater than parameters, we are going to have a stable model. What is the experimental matrix? Okay, here we are going to put all the 8 different combinations. Here we are, okay? So in the first run, I will combine material 1 with the first length, which is 30, and with the first width, which is 16, okay? The second run will consider again material 1, the same length, which is 30, but now the short one. Instead of 16, I will have 10 centimeters, okay? Is the second combination. Then the third combination, run 3, again, material number 1, but now the length is going to change. It is going to be 20 instead of 30, okay? As you can see, it is here, it was 30, now it is 20. But the width is, as in the first case, 16 centimeters, okay? With 3 centimeters height. The fourth combination, you have the first material, but now the short length and the narrow width, okay? Which is 1, 20, and 10. So if you see, I repeat this 4 combination, but now with material number 2. So I am going to have these 8 different combinations, okay? And with each airplane, I will have 8 different airplanes. I will measure distance 1, distance 2, and distance 3. 3 throws, 3 trials for each of the airplanes, okay? Well, this is balanced and orthogonal. This is a very good design. This is a good design of experiment because it's systematic. I am carrying out exactly the same thing for the 2 materials, for the 2 lengths, and for the 2 widths. Exactly the same. This is a good design of experiment. Why this produces significant coefficients? Because each factor varies independently. The interactions can be separated. There is no collinearity. Replication reduces noise because I am going to throw one and once again the same airplane, and effects become identifiable. Okay. Uh, what is the statistical model that I am going to adjust? It is very similar to the one that we did with our experiment in the classroom. And I am going to look for this experiment. I am looking for beta 0, beta 1, beta 2, beta 3, and beta 4, which are multiplied by the material, the length, the width, and the height. I am considered as well the height. This is a good design of experiment because the design is orthogonal, because coefficients become stable and the p-values meaningful. Do you remember the p-values in the previous exercise? They were very high. They were 0.62, 0.67, and so on. I am looking for coefficients in the p-values which are lower than 0.05, which is 5%. So that's it. And the R square increases, which means that the model is a better predictor of distance in this case because I have a good design. So what will be the process for designing the airplanes? Okay, the first step is to choose the very the same design for all the airplanes, the same design for all the airplanes. So what I did here was to look on the internet and I decided to choose this design. So I decided to use this model in order to build all the airplanes. Okay, so the following step was the materials are selected. In this case, I had 2 materials, bond paper and folder. So it is important to guarantee that the size of the materials is similar, as can be seen I used in the office, in my office in the university. I went and I took these materials. I use recycled paper in order to save the planet. Okay, and this is the yellow thing is the folder, and this white thing with some that is printed. These are bond paper. Okay, exactly the same bond paper. Okay, what is the following step? The step number 3 is that the airplanes are folded following the instructions of the selected design. So I started to fold both the folders and the bond paper exactly in the same manner. All of them were folded exactly in a similar way. Then, step 4, the aircraft construction process continues, ensuring that all the airplanes are similar. Design is not a variable in this experiment. Therefore, it must remain constant. So the design is exactly the same. So what I did was I make sure that all the materials are exactly treated in a similar manner. Okay. Step number 5. As can be seen, the material influences the folding process in the airplane. So for me, it was more difficult to fold the folder than the bond paper because of the material. The width of the bond paper uh, make it very very easy to fold, but the folder is somehow it is very hard to fold. It is difficult to fold. Okay, that's why you can see here in this photograph this airplane. It is like open because of the material. Okay. Step number 6. Once the folds are finished on each airplane, they are placed together so that the similarity between them can be appreciated. So I finished the airplanes and I put them together in order to see how identical they look in this case. Okay, so I have the two folder airplanes on the left hand side and the two bond paper airplanes on the right hand side of my desk in the office. Okay. Step number 7. Now each airplane is checked to confirm its exact dimensions. For example, the one in the following image measures 30 centimeters long, 16 centimeters wide, and has a height of 3 centimeters. Here the bond paper is the construction material. So as you can see, I put a ruler here and here, and the idea was to measure. Okay, so this is 30 centimeters long, and this is 16 centimeters in width. Okay, this I had to measure the all the airplanes to make sure that they were similar. This is a proper design of experiment. Okay, you should be very careful when you are designing your experiment and make sure that you are doing every step in the correct manner. Step number 8, then it is verified that the airplane made with the folder has the same dimensions as the one made of bond paper. So here you have. Now, first I had the bond paper and now I have the folder. Okay, so I make sure that they have exactly the similar dimensions. Step number 9, the airplane shown below is the one with short wings, although it retains the same length, 30 centimeters. Its wingspan is now 10 centimeters and it is taller with a height of 6 centimeters. Again, the one made with one paper is checked first. So I check it now with the short wings. Okay, this one has wide wings, to fly, but the other one has got the very short wings. You can see here, this is very short. Okay, this is the bond paper. Step number 3, Then the measurements of the airplane built with folder are taken, and it is verified that it has the same dimension as its counterpart made of bond paper. So look, this is the folder, and again with the wings are very short. So at the very end, to ensure that the design was identical in all cases, it was decided to fold down the nose of each of the four existing planes, and this resulted in the short planes, which are only 20 centimeters. All of the planes that I have shown you so far are 30 centimeters long. What I did was just to fold the nose in order to short it to 20 centimeters. Look, they are exactly the same four airplanes, but the only thing that I did was to fold the nose, in order for it to get shorter. Okay, it is now 20 centimeters length. So from here to there, it is 20 centimeters. Okay, and I have my 8 airplanes. In fact, it was four, right? But since I folded this nose, I have the other four, the four long and four short airplanes. Okay, step number 12, to avoid the influence of air currents, a student in the Master of Science in Engineering program was asked to perform the 24 launches within an office area. A starting line was established from which the flight distances of each aircraft were measured. It should be noted that there were 8 designs, and each was launched 3 times. So this is my student of the master degree program, and she was the one that threw all the airplanes. So you can see here, she's ready to do it. She's doing it in this case, and finally the airplane flew. Okay, and then, as we did in the classroom last week, I took the measure exactly in order to see how far the airplane had flown. Okay. What are the results of the experiment? Well, once the 24 launches were recorded in this table, we can summarize. So the first airplane was made with the bond paper. It had 30 centimeters length and 16 centimeters width. The first distance was 489, the second 491, and the third distance 491. Then the second airplane, material 1, length 30, width 10, first distance 232, second distance 277, and third distance 332. Okay, and so on. So I have the 24 measures recorded in this table, 3 for each of the 8 designs. Okay, so here are my 8 runs, and these are my results of all the trials. To analyze the results, a MATLAB script was developed that performs a linear regressions of distance as a function of the material length and width of each aircraft. This is in Appendix A. It also provides the optimal aircraft design to achieve the maximum possible distance. The results generated with the MATLAB script are. So I did exactly the same as I just explained to you before the coffee break that we had, and carry out this exercise. So this is the model summary, okay? This is the linear regression model. The distance uh, has to do with a linear formula with this, 16 terms in 4 predictors, okay? So look the model. This is the model. These are the coefficients, and these are the p-values. Look, the p-values are not so high anymore. They are much lower than in the previous in the previous exercise that we did um, earlier today. Okay, so look, the width. This p-value is 0.08. Now the material width, it is 0.03. Okay, so these are significant. This one, material width height, it is 0.045. So these quantities are lower than 0.05, which is 5%. These are lower. This is 3.6%. This is 4.5%. Okay, so these are significant. So this is a better model. This is a better model. Why? Because we have an experimental design and we have carried out all the process very systematically in order to get a good predictor model. Okay, and this is what you have to do in artificial intelligence. Design your experiment in order for you to have a very good model for predicting. That will be intelligent. That model will be intelligent because it's very well designed. Okay, so let us continue. Here, well, the R squared is much better than the previous one. The previous one was 37. This is almost double. This is 0.70, which is 70% can be predicted with this model. And the other one was only 37%, almost half of this quantity. Okay. Here are the results. With this model, this is a very big formula. It is like the ones that we put here. So it will be that will be distance equals this coefficient 138 times width minus 111 material times width minus, that will be the model. Okay, that will be the model. I am not to write it down, but you can imagine the model. These are the coefficients. Okay, and these are the results. So the optimal result, the best airplane that I can design following these steps, it should be made of folder, which is material 2. It should be made of folder. Then it should have 20 centimeters length and 16 centimeters of width. Okay? And the height should be 5 centimeters. And this will fly 8 meters. This will fly in total 8.44 meters. Okay? This is the optimal design. If I want to build the very good, the airplane that will win all the throws, always, these are the characteristics. How I know? Because I carried out a very good experimental design, and this is an intelligent model that is providing me with the optimal design of this airplane. Okay? And this is the equation. This is the equation. And well, I can see now the response surface. Okay. The response surface for material 1 is shown below. As can be seen, the optimal combination for bond paper is when you have an airplane that is 20 centimeters long with a wingspan of 16. With this design, you can expect the airplane to fly 5 to 5 centimeters. Okay, and here is the response surface. So you have the combination, this is the length, you have 20 at the beginning, and the width you have 16. This is the maximum, the higher distance that you are going to reach with this design. Okay, with 20 centimeters length and 16 width, you will reach more than 5 meters. Okay, this is with material 1 bond paper. What about Material 2. For airplanes made from folders, the optimal combination is also one where the design is 30 centimeters long and 16 centimeters wide. See the following figure. With this, a flight distance of 610 centimeters can be expected. Therefore, the material that maximizes the distance is the folder. So again, if you have, in this case, this combination, 30 and 16, you can reach more than 6 meters with folder. So folder is better material than the bond paper, right? But if you combine this material 2 with a short distance of length 20 and the width of 16 and the height 5, you can reach up to 8 meters, okay, of distance. So look, we have fitted distance, which depends on material, length, width, and height. So we have 4 main effects, 6 two-way interactions, 4 three-way interactions, 1 four-way interaction, and 1 intercept. So in total, we have 16 parameters. So let us count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different interactions we are proposing in this model. Okay, it's a very complex model, I should say. It's a very complex model because it has a lot of interactions. You can see here material length width, material length height, material width height, another one, material length width height. So you have different interactions, and it is a very complex model. So in total, you have 16, but you have 24 observations because you flew 24 times all the airplanes. So the inference is mathematically valid. You have a model with a good significance. You can see it here. It is lower than 0.05. That is the number that you should keep in mind always. And what is the interpretation? This model is statistically significant, and we reject the null hypothesis that all regression coefficients are equal to 0. That is rejected. So the conclusion is that at least one factor or interaction significantly explain variation in flight distance. That is a very good news for us. And the goodness of it is 0.7. So the model explains 70% of the variability in flight distance. This is reasonably strong for physical experimental data. Okay. Here we have another indicators that we will be explaining in the following weeks and months. But for now, you keep in mind that this is a very good model. And look, the linear effects are significant. Again, this value is lower than 0.05. And the nonlinear interactions are also significant. So in other words, this coefficient with only one variable, they are linear, and the nonlinear are the ones that have 2 or more variables. These are important, these coefficients, and these ones are as well are important. All the coefficients here are important. Okay. Okay. So let us now interpret the coefficients. Okay. So material times width, this is the coefficient, minus 111. So, and this is important coefficient because of this value is lower than 0.05. What does that mean? It means that the effect of width depends strongly on material. Increasing width does not have the same effect for paper than for folder. This is physically plausible. So that means that the folder is very rigid, okay? And the bond paper is very soft. So this means that when I threw the airplane, this rigidity is affecting the flight distance, okay? That is the interpretation of this number, okay? Let's see material times width times height. This is the estimate, and it is significant again. So width effect changes depending on both material and height. This confirms no linear aerodynamic coupling. That means that if I have a very sharp airplane, a very sharp, the one that I built at the beginning, it's a very sharp, that is aerodynamics. So it is better for the airplane to have this aerodynamic aspect than the other with the nose folded, okay? This is the interpretation of this coefficient, okay? Some marginal coefficients is the width. So yes, the width is important, but not so important because this coefficient is not lower than 0.05. This is greater. That is 8, and the other would be 5%. So this is some kind important. This is again some kind important material length and width, but this coefficient is showing that it is not so important. And what is not significant is just to the length and the height, they are not significant. So if you have a very long airplane, it doesn't mean that it will fly longer. Or if you have a very short plane, it doesn't mean that it will fly shorter distance, right? The same happened with the height. The same happened. So they are not simply additive effects dominating. The performance emerges from interactions. The good point here is the interaction. You have to have a good design combining the material, the length, and the width at the same time, the three aspects. The material will not give you a good design, but if you combine again the length and the width with the material, you have a very good design. So, and this is normal in complex systems, okay? Why many coefficients are zero? Because this is because you have a lot of combinations of possible combination, but not all of them are significant. So they are just zero. They are out of the equation. Literally, they are out of the equation, and you just keep the ones that are significant. That's why. Well, this is the MATLAB script. Okay. Okay. Well, this is the proper design of experiment. This is a good model. You can see all the surface. You can see the coefficients. You can see the table when you record all the distances in a very systematic manner. And this is what you have to do when you are carrying out an experiment. You have to plan the experiment. You have to design it using the factors, and you have to follow exactly the same methodology for all the samples that you are going to test, as I did here in this experiment. And this is how you are going to get a very good model. Okay, a very good artificial intelligence model. If it is well designed, you are going to get a very good model for artificial intelligence. This is our model. It's a very good model, excellent model, because it was planned. It was designed exactly as you could see in this class. Okay, here is my matrix. Here are the factors, and this is how you are going to get a very good design. Many companies use this design of experiment. For instance, in order to design a new car, Ford, General Motors, Audi, BMW carry out these kind of experiments, and they play with the aerodynamics of the car. They play with the weight of the car, how heavy it is. They play with so many different factors, different variables. Okay, and they try in a laboratory. They try all these samples, and they get measurements for each to have the performance of the cars, and they can improve security. For instance, in the case of a car accident, they can improve the security of the passengers because they in the laboratory carry out all these experiments. I didn't use a laboratory. I used my office, okay, my office in the School of Engineering in order to carry out this very simple experiment. But as you could see, you can get very good results with this strategy. Okay. Do you have any questions? Is it clear what I have said so far? Okay. So now uh, let us finish this lecture with this explanation, this theoretical explanation. So, a experimental unit is the smallest entity that independently receives the treatment. Okay, so we are going to work in experimental design with this experimental unit. So, for instance, in our case, each individual airplane is an experimental unit. One airplane is one unit, okay? The bond paper airplane with the long distance is one experimental unit. The folder made airplane with long distance, again, is another experimental unit, okay? We have in total 8 experimental units in our exercise. Why? Because each airplane is built from one material. The material treatment is applied to that airplane, and it flies independently of the others. So I have one airplane, I throw it 3 times, and that's independent. That is an experimental unit. So if we build 4 airplanes from bond paper and 4 airplanes from folder, we have 8 experimental units. Okay, what is a sampled unit? The sampled unit is the unit from which measurements are collected. In our case, each distance measurement from a single flight is a sampling unit. But here is the important nuance. If we throw the same airplane 5 times, so I have one experimental unit, which is one airplane. The sampling unit will be 5 distances. So in this case, for each experimental unit, I have 3 sampling units, 3 throws. But if I had 5 throws, it will be 5 sampled units, okay? Okay. How can we use this in intelligent systems? Well, when I have a model, you could see I had a linear model, a quadratic model, a cubic model, a polynomial model, exponential model, logarithmic model. I can have any model, okay? That is the intelligence, the artificial intelligence model, okay? So if I train it, if I provide more information, that means if I throw the same airplane one more time and one more time and one more time, this model will learn more information about the behavior of this airplane. So if I feed all this new information, my model will become better model because it is having more information to predict the distance, okay? So this is very important in intelligent systems. Why did I just use 3 throws for each airplane? Well, because of time limitations, because I wanted to carry out this very quickly. I didn't have more resources to build more airplanes and so on. There are many different factors, but you have a limited sample, okay? But if you have resources to the infinity and beyond, you can have very so many different samples, and it is better for your intelligence model. Okay. Okay. We should be very careful here. For instance, if you treat 5 throws of the same airplane as 5 independent units, don't have that mistakes. So if I have just one airplane and I throw it 20 times, that doesn't mean that I have 20 observations, because the result of this model will be very good for this airplane alone, but I cannot predict the distances of other airplanes, okay? So be careful not to build just one airplane and throw it 24 times. That will be not correct, okay? That will be not correct because I am just looking at one airplane. What I have to do is to look at different airplanes, different experimental units, and have samples of each airplane, not just one airplane and so many different samples. No, that's not correct in artificial intelligence, because the model will underestimate variability and we become overconfident and overfit to airplane specific characteristics. It will be very good model, but just for that particular airplane and nothing else. If I want to predict another airplane behavior, I will not be able to do that. Okay. So in a physical artificial intelligence systems, the experimental unit is often the device, the object, the batch, the environment. This is the experimental unit, but uh, don't be confused. It is not the individual sensor that is reading something. It is not the repeated measurement. That is not an experimental unit. That is a sample. The frame of a video is not, and the time span is not an experimental unit. So another concept important here is data granularity, okay? Sampling units and data granularity, okay. What is data granularity? It refers to the level of detail at which data is recorded. So in our airplane experiment, low granularity implies one average distance per airplane, and high granularity implies multiple distance per airplane. So do you remember that in the classroom, we threw each airplane 3 times, but then we have the best. That is granularity. When I have the three, it is granularity, and when I have just one measurement, that is not granularity. So I have to have more measurements, and it is better for my intelligence system. Why granularity matters? More data points doesn't mean more experimental units. For example, if you attach a sensor to the airplane that records position every 0.1 seconds, you have 3,000 position points from one flight, only one flight. But it is only one experimental unit again. So this is high granularity data, but not more replication. So be careful with that. What is the consequence? If you treat high granularity data as independent, you artificially reduce estimated error variance, which make your an artificial intelligence model look more accurate than it actually is. Okay, so be careful not to confuse these two things. Okay, another concept is the pseudo replication. Pseudo replication occurs when correlated observations are treated as independent experimental units. For instance, repeated throws, so one airplane thrown 5 times, if you treat as 5 independent experiments, you have pseudo replication. That is not correct. Frame extraction, again, if you record a video and you extract 1,000 of frames, you have pseudo replication, okay? Because all the frames come from the same airplane. Again, if you just have one airplane, that is not a very good design because you are just going to have a model that is valid for that particular airplane, not for other airplanes, okay? Okay, and look here, a real failure scenario. Suppose that you train a model, you build a model like the linear model, the quadratic model, only on airplanes that I have built personally. So these airplanes, uh, I can fold with my style. I launch with some particular strength, and it is my technique. But if another student comes and it throws exactly my airplanes, because it is different, this is going to cause some variability, okay? And the airplane will not behave exactly the same as it behaved with me. So it will have a different performance if another person throws this airplane, okay? And that could make my model, my intelligence model, fail because another person is using. The point here is it doesn't matter if person A, it doesn't matter if person B, it doesn't matter if person C uses the model. The model should predict exactly the same, independently of who is using this model. So in order to have a correct experiment, first define the experimental unit. Then control variation. For instance, in our case, we have to keep constant, don't move, the launch angle, the thrower, the same person was the one that threw 24 times the same, always the same person. Indoor environment, all was done in a controlled environment, in an office, and the starting position. All the planes were launched from the very same point. Introduce induced variation. So a variation is the type of material. For instance, bond paper versus folder, right? That I am forcing that. I am introducing that variation because I want to see whether there is a difference in the distance if I change the material from folder to bond paper. Avoid pseudo replication. Do not treat repeated throws of the same apron as independent units. Instead, average repeated throws per apron or use hierarchical mixed models. Okay? Okay. In artificial intelligence, more rows is not equal that more information. So if I have more rows, doesn't mean that I have more information. More granularity doesn't mean more independence, and repeated measurements doesn't imply more replication. Okay. So if I use the correct unit, then I can have a valid inference, I can have a proper variance estimation, and I can generalize my models, my artificial intelligence models. I can generalize to other units, okay? And finally, we have different kinds of variation. One is the natural, for instance, in my case, well, I can have a very small current of wind, right, air in at some point when I am throwing one airplane. So this is like if I throw the airplane, it can move a little bit more because that was this air current. The induced variation, again, is a factor that I am manipulating. For instance, I can have a folder, PET, or bond paper material, okay? Okay. Natural variation, a slight difference in sheet thickness. So the thickness of the sheet can vary, that will be natural. I can have a small weight differences, minor differences in folder precision. When I am folding, I can have 1 millimeter difference from one plate to the other. That is a natural variation. Natural air microcurrents in the room, a slight difference in throwing force. I can throw first very strong and then not so strong, okay? The induced variation, changing in material, modifying the wing length. I am controlling that, okay? Adding paper clips as weight, varying launch angle, 30, 45, 60 degrees. And then I can have a systematic variation, always throwing bond paper first. Uh, do you remember in the classroom we use this random thing in order to choose the airplane? So first it was B2 Spirit, then Avion 2, then SF-26. So it was random. So that is I can have out of the equation this variation, but I can force first the this airplane, the bond paper, then measuring distance with a stretch tape. One material tested near a fan. If you have a fan, you have this fan, you throw the airplane, and this is going to have an impact on the distance, right? Because it is creating more air. And the same person throwing bond paper and different person throwing folder. This is systematic variation. And finally, the random variation, a tiny difference in hand release timing. So I can throw the airplane and I can throw it very quickly or very, very slowly. Random air turbulence, slight random deformation during flight, small reading error when measuring distance, and variability in landing point due to instability. Okay, so to sum up, the we have 4 different variations: natural, induced, systematic, and random. This is not intentional. The induced, yes, it is intentional, but the systematic and random are not intentional. Okay, and here are some examples that we have in the airplane case. Okay, so be very careful in artificial intelligence to control systematic variation, to replicate, to estimate random variation. Uh, you have to block if necessary. For instance, you have to check exactly the moment when the thrower throws the airplane and randomize the run order, okay? That it is random. Okay, so what we have learned here? You should be able now to identify a true experimental design, not just a random design like the one that we did the very first class of did with the material and things. You just design it an airplane and that's it. You have to detect pseudo replication in databases, distinguish natural and induced variation, explain why improper unit definition damages generalization, and understand statistical independence in model training. Okay, this is what we have learned today. I don't know whether you have any question. Let me stop sharing this. Okay, I am going to finish the recording and give me a minute please. I am going to finish the recording. Thank you very much.